Hi, Chem 212 students, and welcome back for our next set of lectures. This week we're going to be talking about infrared spectroscopy and mass spectrometry. So these are two ways that we can characterize the products of our organic synthesis reactions and see if we got the products that we were expecting or what kind of products that we got. Now, when it comes to infrared spectroscopy, this is going to tell us things about which atoms are bonded in our molecule, the infrared spectroscopy, whereas mass spectrometry will give us an idea about how the various parts of a molecule are stuck together. And so let's start to go into this. On the screen here we can see an IR instrument. The ones we have now are even smaller and more compact. They're very nice these days. When I used to take these, they were much bigger. About 20 years ago when I was doing these, there weren't desktop instruments like this, but they're very handy now that we have them. And here's an infrared spectrum. So you guys might have already taken an infrared spectrum in lab, depending on where we're at for the semester. But this tells you a summary of what types of peaks in an infrared spectrum would tell us which types of bonds that we have in the molecule. So let's go back and review briefly what kinds of visible or what kind of light there is on the electromagnetic spectrum. Remember that visible light is actually only a very, very narrow part of the entire electromagnetic spectrum. It's even exaggerated here, 400, 700 nanometers. Really, this spans, very, very long length wavelengths here, from nanometers all the way up to micrometers and beyond for radio waves, even centimeters for some radio waves. This keeps going. So in infrared spectroscopy, what's happening is infrared light in the 2-ish micrometer region, micrometers, is shot at a sample. And when you have matter that is absorbing infrared light essentially is like heat energy. So what happens is that is the energy that is absorbed by most somewhere in this range by most bonded atoms, and that absorption results in an increase in the vibration frequency of the bonds. And we'll talk about how bonds vibrate in and out and in various other ways. And so we perceive that when we feel infrared light on our skin as heat, because it warms up our skin by causing our molecules to vibrate with a greater frequency. And as you can see, there's other regions too, but we're going to be focused on the infrared. So notice that the wavelengths are slightly longer than visible light. They're longer than visible light. The frequency is shorter. These are higher energy waves. Recall that, or the frequency is greater rather. Recall that a greater frequency means more energy. So we have higher frequencies over to the left. These are the more energetic waves. They have these shorter wavelengths. So over on the right, we have the longer wavelengths. So C equals lambda nu, and if we combine these two, we get that E equals HC over lambda. So we can see that a larger wavelength is a smaller energy. Oops, the lambda's down there. So larger frequency equals larger energy. Smaller and smaller wavelength equals larger energy. Smaller wavelength, larger energy. Higher frequency, smaller wavelength, they're higher energy lights. So infrared is slightly lower energy than visible. Now, there's various types of spectroscopy that you're going to study in this class that are useful for characterizing the products of organic reactions. One of them is IR, or infrared spectroscopy, which uses infrared radiation. These will tell you something about which atoms are bonded to which other atoms, or what functional groups you have in the molecule. UV-vis spectroscopy is generally used in order to determine the concentrations of colorful compounds in solutions, or it can also determine if there are conjugated pi bonds. So conjugated pi bonds are those that are alternating double single, for example, in benzene. These have conjugated pi bonds, double single, all the way around the ring. And in later chapters, when you go into Chem 213, you'll learn about nuclear magnetic resonance spectroscopy, which uses radio waves. And this can tell you a lot about the arrangement of the carbon-carbon and the carbon-hydrogen bonds in a compound, which can give you ideas about the structure of the whole compound. So right now we're going to be focused on IR spectroscopy. We're also going to use mass spectrometry, which spectrometry is differentiated by the fact that it doesn't use light. Spectroscopy uses light, and so these use various types of light. But in this chapter, we're going to cover IR spectroscopy and mass spectrometry. So for the electrons in the covalent bonds, they exist in certain vibrational energy levels, and these are quantized, like the energy levels in an atom. So they're separated by gaps of particular energies. And so if a photon of light strikes a molecule with the exact same energy as this gap here, then that light will be absorbed, and you'll get a vibrational excitation, which means that the vibrational speed of the molecule will increase. The frequency will increase. IR light causes molecular vibration, as opposed to, for example, the higher energy lights that we were talking about, like X-rays or gamma rays. These would not just excite the vibration, they would actually break the bond. Those high energy lights, those can break bonds. We'll talk about how UV light can break bonds later on when we talk about radical reactions. Eventually, this vibrational energy is released as heat, and the environment of the molecule gets hotter, and the molecule returns to its lower vibrational energy state. So there's various types of vibration that can occur in a molecule. A bond can vibrate in and out, which we call a stretching vibration. If you have a set of 3 atoms in a series of bonds like this, those can go in the plane vibrating like this. Basically, they can get squeezed a shorter angle and a broader angle like that. In out like that. And there's also out of plane or twisting vibrations. That would be when these 2 atoms come in and out of the page. They're twisting. So it's like the middle one's shaking its hips, basically, and these are twisting in and out of the page here. We'll mainly focus on stretching. These give us the most reliable information about which bonds that we have in the molecule, which types of atoms are bonded. So the energy gap, the vibrational energy gap, will vary depending on what kind of bond it is. And so here we can see that in this example on the right, the vibrational energy gap for carbon and hydrogen is greater than that for carbon and oxygen. Okay, and this makes sense to us if we think about the frequency of the bond being related to the strength of the bond. Also important is the difference in the mass. So you can think of maybe the carbon atom is like, I'm holding onto the carbon atom, and the hydrogen atom is on a spring, and it's bouncing like this, in and out. And so if you had a spring like this, the frequency it would vibrate at would depend on the weight. If you have a very light weight, you can think of kind of like the spring that goes behind doors sometimes. If you pluck that very lightweight, very tight spring with a high bond strength and a very light weight on the end of it, if you pluck it, it will go whoom, and it'll vibrate with greater frequency, and therefore the difference here, that energy will be greater. And so you have a very light weight here with the CH bond, with a very short, strong bond between CH. So there's a large energy gap here. Whereas here for carbon and oxygen, this is a little bit longer of a bond because oxygen is a bigger atom. Also, the oxygen is heavier. And so when you pull on the heavier weight, it doesn't vibrate as much as quickly, even with the same strength spring, right? So if you pluck the very lightweight, it will go boing really fast. But if you pluck the really heavy weight, it would go wah, 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 a lot slower frequency, so a lot smaller of an energy gap. So this is a way that we can make sense of what are going to be the relative energies of light that's absorbed during IR spectroscopy. The stronger the bond, the higher the stretching frequency. That's like a very tight spring. So when you pull on it, it's going to go wing, really high frequency because its spring is so tight, like the spring that holds the door from hitting the wall that you might have seen in some houses. If you have a larger mass difference, you'll also have the higher stretching frequency. So in the difference of the masses here, this will be larger. So here the difference between the carbon and hydrogen atom in terms of mass is much greater than the difference in the masses between the carbon and the oxygen. But here it's the stronger bond, the stronger, shorter bond here that makes a big difference. Okay. So here's an example of an infrared spectrum. Now, instead of showing because of the way infrared spectra are taken simultaneously at many different wavelengths and frequencies of light, a different number is used instead of frequency on the horizontal axis on an IR spectrum. Instead, a amount called the wave number is used, and that is the frequency divided by the speed of light expressed in centimeters. So the wave number unit is expressed as inverse centimeters, with a centimeter here being this unit for the speed of light, and then seconds, 1/seconds canceling. So in terms of units for frequency, a unit is 1/second, and this is going to be over centimeters per second, and so the 1/seconds cancel, and you get 1/centimeters as the unit, well, 1, which is just left of my shoulder here, or 1/centimeters is the same thing as centimeter to the minus 1 power. So you get 1/seconds. I should have written that over here. So frequency over C is 1/seconds over centimeters over seconds. So that is centimeters to the minus 1 power, because the 1/seconds cancel. Like that, 1/second, 1/second, just 1/centimeters, or centimeters to the minus 1 power. Generally, although you might see on the instrument sometimes the peaks can go up, which is measuring the vertical axis in terms of the absorbance of light, usually the peaks are inverted, and the measurement here is percent transmittance. And so when the transmittance is low, that means a lot of energy is being absorbed here. So this is the way that the IR spectra are usually portrayed. And the wave number values tend to range from 400 to 4,000 wave numbers, and the lower number, notice, is on the right here, the higher number on the left. The higher number is really a higher frequency, right? And the lower number is the lower frequency here. So high frequency bonds are over on the left, low frequency bonds are on the right. So we're going to look at 3 important characteristics of each of these peaks. You'll notice some of them differ in terms of what wave number they have for their peak. So here we have this broad peak here with a higher wave number. You can also see they vary in terms of intensity. Some have very, very strong intensity. The peaks are very big, whereas some are smaller. And then the shape. Some are broader than others, and some are very narrow and pointy. And so let's talk about how the type of bond affects each of these factors. So the wave number can be calculated theoretically based on this equation here, which you do not have to memorize, but I will explain it. Notice at the top here is a force constant. So this is telling you something about the bond strength here. And so the larger the bond strength, the larger the wave number. So like a very strong bond between carbon and hydrogen here has a very higher wave number here compared to longer, weaker bonds. So the carbon-chlorine bond is much longer. than a carbon-oxygen bond, for example, and so it's weaker and has a lower frequency. So this is the F here in that. And then the reduced mass here, which is the mass of one of the atoms times the mass of the other divided by their sum. So this is going, so you can see here, this depends on the mass. The mass is on the bottom. So basically, the larger the masses of the atoms, the larger this bottom term will be, and thus the smaller wave numbers you will have. And so for larger, heavier atoms, the wave numbers will be smaller, which makes sense, right? Again, if you have a spring, if the weight is heavy, it's going to vibrate at a lower frequency than if you have a very light weight on the same spring. It will go boing really fast, and it will be a high frequency if it's very light. In terms of the bond strength, also whether it's a triple bond, a double bond, or a single bond will affect that strength of the bond. The triple bonds are generally stronger than a double bond, which is stronger than a single bond. And so stronger bonds between lighter atoms leads to higher frequencies, and weaker bonds between heavier atoms is lower frequency, lower wave numbers. So when we think of what's the highest wave number, then those bonds to hydrogens are going to have a very high frequency because the hydrogen is so light, and also it makes very short, strong bonds. So on the very left, from about 27-ish wave numbers up to about 4,000, all of these will be generally bonds to hydrogen. And then you can see that below those in the middle regions are bonds that are not to hydrogen, but they're triple bonds. Those are stronger generally than the comparable double bonds, so they have a higher frequency, higher wave number, and that is larger than the single bonds, which will end up being in the 1600 to 400 range. And so notice how I don't really need to memorize exactly these ranges, right? As long as I have a sense of generally where they should be relative to one another. On the far left will be bonds to hydrogen, then triple bonds in around the 22-ish, 2200-ish region, double bonds between these larger atoms in the 1700-ish region, and then lower than that you end up in the single bonds lower than 1600. Just know relatively where these are, and you will have this for reference anyway, but you should understand why these lie in the regions that they do. Okay. So when it comes to reading a infrared spectrum, we're going to want to think about where the bonds lie based on what we just saw. In general, we have two large regions we can divide the IR spectrum into. If we're looking at wave numbers 1500 or below, there's often many single bonds between many different types of atoms that will have frequencies, vibrational frequencies that are in this region. And so a lot of the times those peaks will will overlap one another, and they can be hard to distinguish from one another. So this region is often called the fingerprint region because it's all the peaks are overlapping, and although we can't interpret all of them, they do give us a kind of fingerprint that will tell us that if we see another molecule with exactly the same type of pattern in here, it might be the same molecule. Whereas above 1500, we call that the diagnostic region. And here, these peaks tend to be very well resolved, meaning that they're not on top of each other a lot of the time. Sometimes they are, but a lot of the times they're not. And so we can see more precisely and determine what types of bonds these peaks will relate to. So we're always going to be looking in the diagnostic region first, and then we'll see if we can get anything out of the fingerprint region. A lot of the times we can't really. So there are many typical signals in that fingerprint region, as I said, and so this part is difficult to analyze. So we start by analyzing the diagnostic region. So let's take a look at this molecule here. Notice that we have two molecules that both have hydroxyl groups, or OH bonds. There are this one's called 2-propanol. It stands with anol because there's an alcohol, and prop because there's 3 carbons. The 2 because the alcohol is on the second carbon out of the 3, as opposed to 2-butanol, the same thing, but there's 4 carbons on the main chain. So you'll notice If we look at these two molecules in the diagnostic region here, you'll notice they look extremely similar because they both have this large broad peak here, which actually corresponds to the OH. They have these peaks in here, which are corresponding to various carbon-hydrogen bonds. And then they have this and then the diagnostic region, it has a couple of peaks right here. And then after that, there's nothing really else. And these are almost exactly the same between the two molecules. Where they differ is down here in the fingerprint region, right? And doing analysis of what each of these peaks would represent could be quite difficult. But we do see that they differ, so it must not be exactly the same molecule. So let's look first at carbon-hydrogen bonds. So the frequency of the stretching frequency for the carbon-hydrogen bond will vary depend on how that carbon is hybridized. And so we can see that it will be the lowest for sp3 hybridized carbon atoms. It will be a little bit larger for sp2 hybridized carbon atoms, and it will be even smaller for sp hybridized carbon-hydrogen atoms, carbon-hydrogen bonds. And if we think about the orbitals, we'll remember why, right? Remember, sp orbitals are smaller than sp2, which are smaller than sp3. So the carbon-hydrogen bond here is shorter than the one in the sp hybridized carbon than the one in the sp2 hybridized carbon, right? Which is shorter than the carbon-hydrogen bond, the sp3 hybridized carbon. So that would make sense that this shorter bond here would vibrate at a higher frequency than this longer one over here, right? So the higher the S character of the carbon, the stronger the CH bond, so the higher the frequency. So what generally you do is when you're analyzing, and you'll almost always have carbon-hydrogen bonds in your molecule, so you'll always look around 3,000 wave numbers for the various carbon-hydrogen bonds. If we have a sp3 hybridized carbon, peaks for those carbon-hydrogen bonds, which usually there are a lot in any given molecule, you'll see those peaks just below the 3,000 line, wave number line usually. And there are a lot of times going to be many peaks overlapped here because there's often many carbon-hydrogen bonds in a molecule. Then on the left here of 3,000, just on the left around 30, not even 3,100, about 3,050 to 3,100, you're going to see the sp2 hybridized carbon-hydrogen bond. And usually there's fewer of these, so you won't see as many peaks here unless you've got a lot of hydrogens attached to the carbon, attached to the double bond. Here we only have one, so we just get this one peak. And then finally, if you go above 3,200 wave numbers, you get this sharp peak in that region. That'll be an sp hybridized carbon-hydrogen bond. Notice that, again, these peaks here tend to be very narrow as well. We'll talk about the narrowness of the peak in a little bit. We're focused here on the wave numbers. So that's one of the first places you want to check, is you want to check here at around 3,000 and see if those carbon-hydrogen stretching frequencies are below 3,000, all of them, or if there are some above 3,000, which will indicate to you that there are sp2 hybridized or sp hybridized carbon atoms. So it is possible that you can have a carbon-carbon double bond in the molecule, but get no CH stretching frequencies. Or you could have a carbon-carbon triple bond and get no CH stretching frequencies that are above 3,000. This would happen if there are no hydrogens attached to the carbon on the double bond. If it's all carbon atoms, well, then you won't get a carbon-hydrogen stretching frequency because there's no hydrogen attached to any of the carbons on the double bond. Similar thing can happen here for the sp hybridized carbon. If there's no hydrogen attached, you won't get the CH frequency. Now, one thing to note is that the frequency of the stretching will vary depending on if the molecule exists in resonance or not. The carbon-oxygen double bond here is a part of another resonance structure if these double bonds are conjugated, meaning that the double bond has a space here with a single bond and then another double bond. So this causes a delocalization of the electrons because we can have various resonance structures that would arise. We can keep track of our resonance pattern here. Whoops. So the way the resonance pattern would go would be, this is a pi bond between atoms of differing electronegativity, and so we can put the electrons over here, which would give this a negative formal charge, and this would give us a positive formal charge, and this double bond wouldn't be here anymore. And then we'd have an allylic positive formal charge, and we can have a bond there, and then we'd get this structure right here. That. And so this has resonance, and because it has resonance, the bond here is loosened up a little bit. I'd say that's the way I like to think of it anyway. The electrons are not all stuck right here in this double bond. They can move around. So this means this double bond is not a full double bond. It's kind of a little bit weaker than a double bond. And so you can see that the stretching frequency for this carbon-oxygen double bond is lower than the stretching frequency of this one. So the resonance environment can affect the wave numbers, the frequency that you see a certain bond at, a little bit. So what's going on here? Well, what else is happening here in terms of when an infrared spectrum is being taken? What's happening to the bonds? Well, when we do hit that molecule with the exact correct frequency of light to promote its vibrational energy from one energy level to the next one, the atoms there are going to be stretching in and out. And so all these atoms have different pulls on their electrons, so they have different electron environments. And so when you have a polar bond and it vibrates in and out, this itself induces its own electric field. And so the result is that you get a variation of that dipole moment in the bond. Whereas when it's longer, it's a bigger dipole moment. Whereas it's shorter, it's a smaller one, and over time this goes up and down. And so that causes an electric field to surround the bond. And the result here is that you get, with greater bond polarity, you get a stronger IR signal. So here we can see if we have a carbon-oxygen bond, these are two atoms that are very different in electronegativity. And so when that bond vibrates, you get a very different magnetic field here when that bond is vibrating. Whereas a carbon-carbon atom, there's basically no difference in electronegativity. So you get a smaller interaction with this electrical field here. So there's this like electromagnetic field that's produced because of this movement of charge, kind of like when you have electrons moving along a wire, if you've learned that in physics class. So the take-home message here, though, is if you have greater bond polarity, you're going to have stronger IR signals due to this. So here we can see the difference. When we look at the intensity here of the stretching for a carbon-carbon single bond, we get a much less intense peak here over here around, so all of these double bonds happen around 1700-ish. So you can see that the carbon-carbon double bond here, it's a little bit lower in frequency because the atoms are lighter, and it's lower in intensity because the atoms are closer to, they're the same, they've got the same electronegativity, whereas carbon and oxygen don't. Oxygen is a larger atom, so in terms of the wave numbers, it has a higher frequency, higher wave numbers. And in terms of the intensity is greater because the atoms differ more in electronegativity. They differ quite significantly. So the more polar the bond, the more intense of a signal you're going to get. You'll also get more intense signals when you have more of the same bond. So if we have many carbon-hydrogen stretches or many carbon sp2 hybridized carbon, this peak could get more and more intense. Every time you get another carbon-hydrogen stretch, it will add to the size of this peak. So these peaks will get larger when you have more polar bonds. They'll also get larger when you have more of the same types of bonds. So although carbon-hydrogen bonds are not very polar, they can give large signals because often there are many, many of them in a molecule. So that's something you can see right here, for example. So with this is, notice that if we draw a line here at 3000, we can look and see, oh, in this molecule, what kind of carbon-hydrogen bonds do I have? Well, if I draw the line at 3000, like right there, 3000, we can see that all of these carbon-hydrogen stretches are below 3000, so they're all sp3 hybridized carbon CH stretches. And so we can tell that we can tell that we have no sp2 hybridized carbons with a CH bond here. But the peak is very intense, and that tells us we have a lot of these CH stretches. Notice here, if we're looking for a carbon-carbon double bond here, we had no signal here for this particular molecule. Why is that? This has to do with the complete symmetry of the molecule here. And so the way that we get a signal is by the absorption that occurs when this light comes in and excites the vibration of the bond, and you get this kind of offset to the distribution of the electrons, which causes the absorption here of this light. But here, because of the complete symmetry around the carbon-carbon double bond, we have no carbon-carbon double bond signal here. So if we have a double bond in a molecule here where it's completely symmetrical, you won't even observe the peak if the molecule is completely symmetrical around the bond that you're looking for the frequency of. So that can also affect the intensity. Now, so we've talked about the wave numbers, the frequency, we've talked about the intensity, and now we're going to talk about the last characteristic of the signal, which is the shape. So you might have noticed that some of the absorptions here had very narrow peaks that look like teeth here, whereas some have very broad peaks here that look like these bumps. And so the question is, what's causing that there? Generally, we see very broad peaks like this in OH stretching signals. We also see them sometimes in NH stretching signals. So these peaks arise because if you have a molecule, for example, like ethanol here, which has OH bonds, these can hydrogen bond to their neighboring molecules. So we have this oxygen atom in the OH bond. The oxygen atom is partially negative. It's pulling electrons towards itself, which causes this hydrogen over here to be partially positive. Now we have the same situation happening in a neighboring molecule where the oxygen is pulling all the electrons towards itself, so it's partially negative. So we get this attraction here, and that stretches this bond. It pulls on it, and when it pulls on it, depending on how close this hydrogen is to the neighboring molecule, this bond will be shorter or longer depending on how strongly it's pulled. So for that reason, all these various ethanol molecules will give an OH stretch at a slightly different frequency because it depends on the local environment of the molecule and how close it is to the neighboring molecule at that moment. And so that's why you get a kind of range of frequencies for molecules involved in hydrogen bonding like this. The more the bond is being pulled and tugged at by these dipole forces, the broader the peak will be, because each of those atoms will have various bond lengths and will be vibrating at slightly different frequencies. So notice that this is only true if these alcohol molecules are close to one another the whole time too. So if you dilute the alcohol in another solvent that doesn't have this kind of hydrogen bonding, then the peak will be narrow at that point. But when it's all alcohol here, that OH peak will be broad because of the extensive hydrogen bonding. So here we can see two various OH groups here. We have two signals for OH bond. One of them is a free OH that's not being involved in hydrogen bonding. You can see it has a narrow peak here at a higher frequency. because its bond isn't being pulled and lengthened. Remember, longer bonds or weaker bonds are going to vibrate at uh, the shorter frequency here, or the yeah, and this will be the smaller frequency rather, and this will be the higher frequency here, the free OH that isn't getting tugged on. But you can see for the OH participating in hydrogen bonding, the frequency can vary quite a lot depending on the local environment of the molecule and how close it is to a neighboring molecule. And right. One thing to note here, and you'll have to watch out for this, if you have a OH bond that's involved in a carboxylic acid group. So the carboxylic acid group, if you have forgotten what it is, it looks like this. So here we're going to have a hydrogen that can participate in hydrogen bonding. Also, though, it's involved in resonance right here. There's resonance that can go on for this structure. And so remember, previously we said that if we're measuring frequency of a bond that's involved in resonance, then that will cause the frequency to shift to a lower frequency. And we can see that right here. The OH from the carboxylic acid shifts to a low frequency and starts to overlap with the carbon-hydrogen bond peaks that happen around 3000. And so you can see it overlaps right with them. And so when you see a downshifted OH bond here like this, that's indicating to you that it's involved in a carboxylic acid. And you can verify that because you're also going to see a carbon-oxygen stretching frequency that occurs at around 1700 due to this carbon-oxygen bond right here. And so when you see that pairing of a downshifted OH, broad OH, along with a intense and broad carbon-oxygen double bond peak at 1700, that is telling you that you have a carboxylic acid functional group in your molecule. And again, here we have very pronounced hydrogen bonding in the carboxylic acid because we can get two hydrogen bond situations in the same molecule here. This hydrogen is partially positive because the electrons are being pulled this way. This oxygen is partially negative, so there's an attraction here. This hydrogen partially positive again because the oxygen is pulling the electrons away. This oxygen partially negative due to the electronegative oxygen. So you get very strong hydrogen bonding interactions here. And so that broadens this peak over on the left. That broadens this peak even more right here. See how broad it is. Let's talk about NH stretching signals now. So these can also be broad too for the same reason. We know oxygen, hydrogen, and nitrogen hydrogen bonds can participate in hydrogen bonding. In addition, there's going to be another situation that we observe that's special in primary amines, and that is that because these NH bonds can be involved in hydrogen bonding, they have these broader peaks. But also, if we have a primary amine, we're going to get two peaks, one for each of the hydrogens. They're going to be each in their slightly different environment, so it's going to yield two separate peaks if the nitrogen is primary. And what we mean by primary is it's attached to one other carbon and two hydrogens. Whereas secondary amine, so the one on the right here, which is attached to two carbons. So for the secondary amine here, what we can see is that we have only one peak, and that peak is broad, of course, due to the hydrogen bonding. And that's because there's only one hydrogen. And so obviously that hydrogen only has its own environment, but that environment does vary due to its participation in hydrogen bonding. So when these two nitrogen hydrogens vibrate together, they vibrate in different ways. So this is going to be an explanation for why for the primary amine we got two peaks here. They can vibrate in terms of a symmetrical stretching. And this is where they're going in and out at the same time. So they're both going in at the same time, they're both going out at the same time. There's also an asymmetrical stretching here. So here's where one goes in while the other goes out. So the symmetrical stretching would be like this: in, out, in, out, like that. Whereas anti-symmetrical stretching will be like in, out, like that. Um, and so because there's two different modes of vibration here, stretching vibrations, we get two different types of peaks, two separate signals, only when the nitrogen is primary and attached to two hydrogens. Um, Now, I'm going to give you a summary, a more complete summary. There's a good summary too in table 14.2 of your book, but I'm going to hand out to you a summary of where all of the peaks lie, and it will include this table in general. So general regions where you'll most likely see peaks that correspond to certain types of bonds between atoms. And often, if the molecule is simple enough, we can identify the entire structure from the IR. For more complicated ones, we do often need complementary techniques such as mass spectrometry or NMR spectroscopy. But we can get a lot of information about it out of just an IR spectrum. So we want to start, we're going to use these steps to analyze the spectrum. First, take a look at the diagnostic region and check to see if there are any double bonds. You'll find those around 1700. Then check for triple bonds. You'll find these in the range of about 21 to 2300. Then check for the various bonds to hydrogen. And that includes checking the carbon-hydrogen bonds, of which there can be three types, remember. Also, we'll look for OH and NH. And those tend to give the very unique signals that we were talking about before. The CH ones, remember, you want to check around 3000 and see if they're above 3000 or below 3000. Then once we've identified the relative wave numbers for the peaks, we want to analyze those wave numbers and also take a look at the intensity and the shape to give us a little bit more information. So let's say we are analyzing this spectrum. We're looking at the diagnostic region, so we're all definitely above 1500. And so we've cut off here below about 2700. So if there were double bonds, the double bonds would be somewhere in here, but there must be no double bonds here. So we're looking at the rest of this area, and we see that if we were to have, we've got here, what we can see is if we look around 3000, all of our peaks here are below 3000, indicating we only have sp3 hybridized carbon-hydrogen stretching signals. And so we don't have any indication here of a carbon-hydrogen bond for a carbon that's on a double bond, or a carbon-hydrogen bond for a carbon that's on a triple bond. We also don't have any peaks around 3300-ish, no NH stretching peaks. We also don't have any 3500-ish OH stretching. These would be broad peaks that would be quite intense, but we don't see them. So this must just be mostly hydrocarbon. Now, why do we use IR? How will we use it in the lab as we move forward and as you go into Chem 213? Well, when you conduct a synthesis, usually you're trying to get a particular functional group on the molecule. You're trying to perform a reaction that will get you a particular functional group. For example, we'll learn later about how if we oxidize an alcohol, that will mean that it turns to a carbon-oxygen double bond. And the peak for the alcohol here, we would see a broad peak around 3500 due to the OH bond if we have the reagent molecule. But however, if we've produced our product and we've used up all of the reagent molecule or most of it, we should not see a significant peak over for 3500 for OH stretching. We should, however, see a peak around 1700-ish with a carbon-oxygen double bond stretching. And so we can use IR to determine if our reaction was successful, if the reactant was consumed, and if the product was produced. And so in terms of your looking for your peaks, those are all the factors that you're going to use. Mainly what you'll be doing as we go through the week is completing a packet, which is homework 10, which has various IR and mass spectra that we will use in order to practice for this. Your book doesn't have a whole lot of practice problems. So I've got some, let's see, some additional notes here that I'll be handing out to you. Uh, these notes look like this. One. These notes look like this. IR spectroscopy summary here. And so we can see that in IR spectroscopy summary, I summarized here the three important properties of spectral peaks. This is a general summary of where you will find those peaks, specific patterns to look for as they relate to carbon-hydrogen stretching, OH stretching, double bonds, carbonyl, which is C double bond O, which is slightly higher here due to the polarity of the bond in frequency than the non-polar carbon-carbon bond. And finally, the double peak that you get around 3500 for the primary amine versus the one you get around 3500 for the secondary amine. And this is the general regions where you'll find the bonds, and then more specific frequencies for various bonds. And so this is table 14.2 that I mentioned. And so you'll use this to analyze a variety of spectra, and their homework this week will be related to that. As we go into the next video, we're going to talk about mass spectrometry, and I'll have a similar summary sheet here for mass spectrometry that you will use to help you analyze the peaks, and we'll have all the steps here that you would need to analyze the mass spectral peaks. So next time we're going to go into mass spectrometry, so I'll see you in the next video.